So today we're going to discuss carbocation rearrangements, namely hydride shifts and methyl shifts. So let's jump in and look at the outline for the discussion. We're going to learn today, first of all, is what a carbocation is, how they're formed, what makes them stable, and different ways to stabilize carbocations. And then that's gonna lead us into the discussion of rearrangement, which is one way that carbocations are stabilized. All right, so let's jump in and talk about what a carbocation is. It's a compound word, carbo for carbon, cation meaning that is positively charged, right? And then the way carbocations are made is by taking electrons away from carbon, right? Both electrons. If carbon has a full octet and you break one of its bonds, you're going to remove both electrons from carbon, and that's going to cause carbon to have a positive charge. So you can see right here, right, I'm breaking the bond between carbon and iodine, and in doing so, I generate a carbocation and an iodide anion, right? So carbocations result from broken bonds to carbon, right? So let's talk about carbocation stability. I have here on the screen a tertiary carbocation, which you can see has three carbon substituents around the carbocation. And then I have a secondary, which you also notice has two carbon substituents around the carbocation. And the primary only has one carbon substituent, and then the methyl has no carbon substituents. No, what you'll notice is as you decrease the number of uh, carbon substituents around the carbocation, you also decrease its stability, right? So the tertiary is the most stable of all of the carbocations depicted, and the methyl is the least stable. And you can see that the methyl has no carbon substituents, whereas the tertiary carbocation has three carbon substituents. So let's deal with that. The carbocation depicted here is a tertiary carbocation, and the way it is stabilized is that the dipoles of each carbon-carbon bond are polarized towards the carbocation. So the electron density, or the electrons in each one of those carbon-carbon bonds, those electrons are being pulled towards the carbocation, right? Those carbon-carbon bonds are electron rich. So you're pulling electrons towards the carbocation and at the same time causing it to be more stable, because what you're doing is you're decreasing the amount of charge on carbon, right? And that is a good thing, because a charged atom is unstable relative to its neutral counterpart. So with these three carbon-carbon bonds shown here, those dipoles are pushing electron density towards the carbocation and stabilizing it. With the secondary, notice you lost a carbon, right? So that carbon has been replaced with a hydrogen. So now you only have two carbon-carbon bonds feeding into the carbocation, right? And with the primary, you only have one carbon feeding into it. So you can see that the dipoles help to stabilize that carbocation, and the less carbon substituents you have, the less you have, the less electron density you have around the carbocation, right? And when you start removing electron density from around that carbocation, it becomes less stable, right? So carbocations, in this case, this particular type of stabilization, we call it hyperconjugation, where those electron-rich carbon bonds feed into that carbocation, thus stabilizing it, because you're decreasing the charge on that atom, right? You can also stabilize carbocations through resonance. So you see here, this is an allylic carbocation because it's adjacent to an alkene, and the arrow shows that the pair of electrons in that pi bond are moving between these two carbons that I have highlighted. And when that happens, I get a new carbocation, and now the positive charges on a different atom. So resonance allows me to share that charge over multiple atoms, thus stabilizing it. Or I can just do a reaction. I can take the carbocation and react it with a nucleophile, right? Give it some electrons, form a bond. Everything is neutral. Everything has a full octet, and you're done. There's one other way that I want to talk about carbocations being stabilized, and that's through rearrangement. So we talked last week about the different types of reactions, right? We talked about substitution, which is the replacement of a leaving group by an incoming nucleophile. We talked about addition. We talked about uh, elimination, which is the loss of a leaving group to form a pi bond. Addition is when you react a pi system with a nucleophile and you end up breaking the pi bond. Uh, Rearrangement, we haven't talked about. We talked a little bit about it in class today. We're going to talk in more detail about it here, right? But that's the movement of atoms or electrons across a molecule to generate a new structural isomer, right? So let's get to that. But before, I want to show you an example of each reaction, right? So substitution, you can see here the bromine is my leaving group, methyl sulfide is my nucleophile, and that methyl sulfide in the product, you can see it replaced bromine. Same thing with addition. I have a carbonyl. I'm taking methyl sulfide as my nucleophile. It's going to attack the carbonyl carbon. And then in the product, you see that there's now a new bond between sulfur and the carbonyl carbon. And then with elimination, you can see the arrows. I form a pi bond between oxygen and carbon, and then I remove or eject the methyl sulfide, right? So elimination and addition are the reverse of one another. And then rearrangement, if you notice here, the positive charges on a primary carbon, which is horrible. The hydrogen that you see there migrates to that primary carbon. That's why it's a CH3 in the product. But then you also notice now the positive charge is on a tertiary carbon. So we're going to look at two examples dealing with this rearrangement and migration. And we're going to look at a hydride shift and a methyl shift. So let's jump in and do that right now.